using carbon as our model. As a single atom, not bonded to anything, carbon has 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. This electron configuration is the energy arrangement of carbon's electrons. However, carbon rarely exists in nature as an individual atom except momentarily while undergoing chemical reactions. Carbon exists with its valence electrons bonded to other atoms. When carbon bonds to 4 other atoms, carbon's 4 bonds are experimentally seen to be equivalent. And so when the carbon atoms finds itself in a bonding situation, its bonding electrons themselves exist at equivalent energies, which requires that they hybridize to an energy that is intermediate between the 2s energy and the 2p energy. Or you can think of it as a blending or hybridization of the 2 energies, the s and p energies. And since the energies of these electrons have now changed, the shape of the orbitals they occupy are different as well, which we will see momentarily, and those are called hybrid orbitals. They are named 2sp3 hybrid orbitals. The naming often trips up students, so before we go any further, let's take a look at where the 2sp3 name comes from. The 2 comes from the second principal energy level that the valence orbitals are in. The s comes from the 2s orbital contributing to the hybridization, and the p comes from the 2p orbitals contributing to the hybridization, and the 3 comes from the number of 2p orbitals used in the hybridization. Once hybridized, the 2s and 2p orbitals no longer exist, and so we have 4 2sp3 hybrid orbitals. 4 2sp3 hybrid orbitals derived from combining the energies of 1 2s orbital and 3 2p orbitals, which gives a total of 4 2sp3 orbitals. Before we look at the shape of hybrid orbitals, it would be helpful to briefly review the atomic orbitals. The 1s orbital is a sphere, the 2s orbital is a larger sphere surrounding 1s, and here we will get rid of 1s since we are only concerned with the valence electrons. Each 2s orbital is a 2-lobed shape converging at the nucleus. So there are the 3 2p orbitals. However, when hybridization occurs, the s and p orbitals cease to exist, and the 2sp3 orbitals have an entirely different shape. We can see that orbital hybridization explains the VSEPR placement of carbon's 4 valence electrons. Since all 4 2sp3 orbitals are equivalent, each 2sp3 orbital repels the others with equal force, resulting in identical bond angles. The carbon atom only hybridizes when it is in a bonding situation. Here, 4 hydrogen atoms bond to carbon by overlapping their orbitals with carbon's hybrid orbitals. So what would be the reason for this? If we go back and see that both carbon and hydrogen have unpaired electrons, the overlap allows the electrons to pair and thus go to a lower potential energy. The illustration here contains the valence electrons of both carbon and hydrogen, and since everyone likes to visualize atoms as spheres, we can do the same. Here is our carbon atom, and here are the hydrogens with the overlapping spheres, indicating the overlapping orbitals that constitute the bond. The bonds are more readily discernible in a ball and stick model, which also makes the bond angle more visible. Since all 4 sp3 orbitals are equivalent, each bonding orbital repels the others with equal force, resulting in identical bond angles. The bonds in hybridization also have their own nomenclature. The overlapping orbitals are called sigma bonds, which represents the single bond occupied by a single pair of electrons. What about double bonds? How does the hybridization model explain double bonds? We will use ethane, C2H4, to see what happens in a double bond. The single bonds we know are sigma bonds, and the double bond also has a sigma bond, but the second bond of a double bond is a pi bond. Let's see how hybridization and orbital overlap can explain a double bond. The 2 carbon atoms in ethane are equivalent, so let's look at one of the carbon atoms first. A pi bond comes from the overlap of unhybridized p orbitals, and so the atom hybridizes only 3 orbitals, leaving a p orbital unhybridized for the pi bond. The hybrid orbital is called 2sp2, the superscript 2 denoting that only 2p orbitals have contributed to the hybridization. The 2sp2 hybrid orbitals exist in a plane perpendicular to the unhybridized 2p orbital. Let's remove the 2p orbital for now to more easily see that. The 2p hybrid orbitals are spread out at a 120-degree angle, which means that they exist in a plane, and the plane is perpendicular to the unhybridized 2p orbital. So this is what both carbon atoms do when bonding occurs in ethane. Each carbon atom is sp2 hybridized. The sigma bond occurs with 2sp2 orbital overlap. What about the pi bond, the second bond of the double bond? Previously we said that it comes from the unhybridized p orbitals, which we see here from both carbon atoms. The top and bottom lobes of the 2p orbitals overlap above and below the axis of the sigma bond, forming a single pi bond, the space in which the now paired electrons move around. The ball and stick model shows this double bond with 2 dashes. To summarize, sigma bonds occur along the axis between nuclei. The pi bond occurs above and below the sigma axis where the p orbital lobes have overlapped. The ethane molecule also bonds to 4 hydrogen atoms by overlapping with both carbon's other 2sp2 hybrid orbitals, creating 4 more sigma bonds. In the ball and stick model, we can readily see that each carbon has a trigonal planar geometry, and thus the whole molecule exists in a plane with the single pi bond above and below that plane. Now let's look at how hybridization can be a model for the triple bond using ethyne C2H2. The carbon-hydrogen bonds are sigma bonds, and the triple bond is 1 sigma bond and 2 pi bonds. Let's see how hybridization can accommodate this. Since pi bonds come from p orbitals, and we need 2 pi bonds, then 2p orbitals have to remain unhybridized, and so the remaining single 2s orbital and a single 2p orbital will hybridize to 2sp hybrid orbitals. And there is also the violet 2px and the blue 2py orbitals. Here each green lobe is a single orbital, and so they each have an electron, while both violet lobes constitute the single 2px orbital with a single electron, and both blue lobes constitute the single 2py orbital with a single electron. The other carbon in C2H2 also has that same triple bond, and so it has the same hybridization. Let's see what happens during bonding. sp orbitals from both carbons overlap, forming a sigma bond. The upper lobes of the blue 2p orbitals overlap, as do the lower 2 lobes, creating the first of the 2 pi bonds. Can you guess where the second of the 2 pi bonds comes from? Yes, that's right. It is the overlapping of the violet 2p lobes. Let's get rid of the sigma bond for a moment to take a look at something interesting. Each pi bond lies on a separate plane, and the 2 planes are perpendicular to each other, and so the 2 pi bonds are perpendicular to each other. Finally, 2 hydrogens will overlap with the remaining sp hybrid orbitals, creating the C2H2 molecule. The overlap of the space-filling model reflects the overlapping orbitals, which is also represented by the ball and stick model. In the remainder of the video, we will look at hybridization of nitrogen and oxygen using NH3, ammonia, as our model for nitrogen hybridization, and H2O, water, for our oxygen model. In NH3, nitrogen has 3 sigma bonds and a lone pair. So how does hybridization account for this? The hybridization is 2sp3, and nitrogen has 5 valence electrons, so one of the 4 2sp3 hybrid orbitals has a pair of electrons. The 3 sigma bonds come from the sp3 orbitals with a single electron, so they can pair up, And so the remaining electron pair is a lone pair, an unbonded pair of electrons. As with sp3 hybridization in carbon, nitrogen's hybrid orbitals spread out in a tetrahedral shape. And lastly, water. Here, oxygen has 2 sigma bonds and 2 lone pairs. In water, oxygen is also 2sp3 hybridized, but with 6 valence electrons. 2 of the sp3 orbitals have paired electrons. You can probably guess that the sp3 orbitals with a single electron will overlap with hydrogen, and the remaining 2 pairs are unbonded. They are lone pairs. Again, oxygen's hybrid orbitals spread out in a tetrahedral